Okay, 12.2 is a neat little section that deals with liquid properties that depend on the strength of intermolecular forces. We already talked about how intermolecular forces determine the melting points and boiling points. Well, for liquids, they determine a number of other properties as well. So the first is viscosity. So viscosity is the resistance to flow that a liquid will exhibit. And this is probably really familiar to you, like if you compare pouring out a glass of water versus pouring out a glass of maple syrup versus pouring out a glass of honey, right? That each of those is going to have a very different resistance to flow. Water will flow right out. The maple syrup will maybe be a bit sluggish. And the honey, you might actually have to sit there for a few minutes and shake it a bit in order to get the honey to flow out of the beaker. And so they have different levels of viscosity. The honey has a high viscosity and the water has a low viscosity. The thing that determines viscosity is intermolecular forces, right? So we can look at those three things, water and maple syrup and honey, for example, and we'll see that honey has a higher strength of intermolecular forces than regular water does. And we can even go to things lower than water, something like acetone. If you've ever used acetone like as a nail polish remover or a cleaning solvent of some sort, then you might have noticed that it actually flows even more freely than water does. Well, acetone just has dipole-dipole interactions, while water has hydrogen bonding. So the acetone has the lowest viscosity or the least resistance to flow of all of these. Okay, so that's the first one. And we also have surface tension. So surface tension is an actual physical tension that seems to be acting on liquids. And you can see surface tension in action in a number of different ways. If you drip water slowly on a penny or a coin of some sort using a dropper, then you'll see the water forms a dome. It doesn't just flow off of the penny. Instead, there seems to be some force that's holding it together, forming a dome. Or if you very carefully place an unfolded paper clip onto the surface of still water, then it will float, even though gravity is pulling it down, and we know that paper clips have a higher density than water. There is some force that's keeping it up, and lots of bugs, if you go to a lake and you see bugs that stand on the surface of the water, they're also taking advantage of surface tension to not sink and drown. So what is surface tension? What causes it? It actually can be explained from a microscopic perspective. If we look at a beaker of water and recognize that it's made up of little tiny water molecules, and the water molecules that are at the surface are a little bit in a different situation than the water molecules down deep in the middle of it, what we'll call the bulk. So water, remember, has these strong hydrogen bonding intermolecular interactions, and the water at the surface doesn't have as many neighbors. It's got water molecules to either side and beneath it, but up above there's only air. And so it has fewer of these attractive intermolecular hydrogen bonds. Water in the bulk is surrounded by other water molecules on all sides. And so it has a maximum number of hydrogen bonds formed with neighbors. And this is important because those attractive forces lead to a decrease in the overall system energy. Forming new hydrogen bonds is energetically favorable. It lowers the overall system energy. And so we can think of this as having a sort of a cost associated with surface molecules compared to bulk molecules. Bulk molecules are lower in energy and surface molecules are higher in energy, and so the natural tendency is to minimize the number of surface molecules and maximize the number of bulk molecules. Well, that's ultimately what causes surface tension. If you think about what we see with the paperclip and with the dome of water on the penny, if you kind of look at that, in every case what is happening is that by rigidly maintaining this rounded curved surface, the surface area is being minimized. If you were to take water from that penny and instead spread it out flatly, then it would have a much higher surface tension than if it balls up and forms a dome on top of the penny. And so that is surface. That is a surface tension. If you have water that is not touching anything, then it's going to minimize its surface area by forming a sphere. And you can see plenty of videos of like astronauts on the International Space Station playing with water and other liquids, and in the absence of gravity and any other forces, it will always ball up to form a perfect sphere. But surface tension can also have another little bit more complicated effect here. If we think of water in contact with another substance, then it could be that instead of forming hydrogen bonding interactions between water molecules, it will form more favorable and attractive forces with whatever it's in contact with. And so here, let me actually get rid of this, and we'll introduce two new terms: adhesion and cohesion. So adhesion is the attractive force between the liquid and whatever solid it is in contact with. Cohesion are the forces between individual liquid molecules, so liquid to liquid. Right, so water has some attractive forces to other water molecules, those hydrogen bonds. That leads to some cohesive force. But water also may be attracted to glass. If you're storing water in a beaker or some glass vessel, there are some adhesive forces, water attracted to the solid glass walls of the vessel. And so that can lead to some very interesting phenomena. If you look at the water in a glass tube on the left, you'll notice that the top of the water is curved downward. It's concave. And the reason is that the adhesive forces between water and glass are actually more energetically favorable than the cohesive forces. The water is going to try to minimize its energy by creating as many water-glass interactions as it can, and so the water molecules are actually going to climb up the wall of the glass and lead to this sort of curvature that we see. That curvature is called a meniscus, and for water in glass, it is a concave meniscus. We see an opposite effect when we have mercury in glass, say in a thermometer. Mercury has very little adhesive force with glass, and it has a high cohesive force with itself. And so here we'll see the mercury kind of shying away from the glass and forming a convex curvature. And this is just trying to minimize the surface area or the area of contact between the mercury and the glass. The mercury atoms are going to flee away from that glass wall and bunch up in the middle, causing that convex meniscus. And so that is what you'll see in something like a mercury thermometer. So just at a glance, we can look at these two cases, and let's suppose it wasn't water and mercury, but some new substance, and we can tell the relative strength of adhesive versus cohesive forces by looking at the shape of the meniscus, whether it bends downward in a concave fashion or bends upward in a convex fashion. Okay, and then last we have capillary action. Oops. Capillary action. And capillary action is really just an example of what we saw with the glass water adhesive forces. Let's put them up there again. The water wants to climb up the walls of the glass tube, and what ultimately prevents it from climbing up forever is the force of gravity pulling that water downward. But if that tube were to get smaller and smaller and smaller, here we go, sorry, more and more narrow in its diameter, eventually it would reach a point where actually the glass is able to draw the water up. The water will automatically climb up the glass even against the pull of gravity, and the reason it does that is to maximize those energetically favorable water-glass interactions. So capillary action is the result of strong cohesive forces and a sufficiently narrow diameter for the glass vessel. Capillary action is essential to life. It's used in plant tissues to move water around. If you've ever gotten a blood draw, they will often prick your finger first and suck up the blood into a little glass capillary to test your iron levels and things. Capillary action is actually why towels, paper towels and cloth towels, are able to do the job of drying you off or drying off your countertop or whatever, because those towels have a lot of narrow spaces that have a ton of surface area and are able to draw in the water through this capillary action and consequently dry off whatever surface you're rubbing the towel over. So anyway, this is kind of a short, fun little section, just some of the like physical properties and the consequences that come from having different intermolecular forces, and viscosity, surface tension, and capillary action are the three that you need to know.